Okay, well, welcome to Casual Friday Home Edition of Linear Algebra and Differential Equations, coming to you from the third floor of our house in a makeshift office that happened because of spring COVID-19. Anyway, let's just give this a shot and see how it goes. So, what do we have? Last time we were talking about eigenvalues and eigenvectors, right? This is the equation for eigenvalues and eigenvectors. We're going to solve ax equals lambda x. A is an n by n matrix. X is an n by 1 column vector. Lambda is a scalar that may be a real number, maybe a complex number, and this x is the same x as that x. And if we can find these pairs, scalar vector pairs, lambda x, then for a matrix A that makes the action of matrix multiplication on X be the same as just a nice scalar multiplication on X, then we call those things eigenvalues and eigenvectors of A. Obviously, X equals 0 always satisfies this. 0 is not an eigenvector. And so we derived then from this equation, and this equation, and why they matter, right? We did that last time, so go check out that if you weren't there. So this equation is the equation that we will use in order to find the eigenvectors x that live in the null space of A minus lambda I, right? That's really what that's asking. Just because that's a lot to write, we're just going to end up giving that another name as well. We're going to call that the eigenspace of lambda, okay? The eigenspace of lambda. It's also a nice vector space. And we'll denote it E sub lambda, okay? And then we all know what we're talking about. That's going to be the set of all x, right, that satisfy A minus lambda I x is 0, or that the matrix multiplication of A minus lambda I times that x maps things to 0. And then we have the all-important determinant equation, the characteristic polynomial of the matrix A, the characteristic equation, same kind of terminology that we saw in differential equations. That's for a reason. And that guy, the determinant of A minus lambda I, equaling 0, we argued from our nice work on determinants and inverses and unique solutions. And what we were looking for, that this is the condition that we would need to determine non-zero x's as eigenvectors. All right, that's the recap. Here we go. And what did we end with last time, right? Through the magic of movies, here we go. Last time we started with this example, a coefficient matrix A that's a 3 by 3. We looked at what A minus lambda I meant. We went through all of that last time. We computed the determinant using cofactor, the determinant of A minus lambda I using cofactor expansion. We eventually got the polynomial factored into this nice form, 1 minus lambda times lambda minus 2 times lambda minus 3. And therefore, right, this guy equal to 0 shows our characteristic polynomial. Gives us that the eigenvalues of A are lambda equals 1, 2, and 3. Okay, lambda is the pretty much favored variable to use or letter to use for the eigenvalues. Of course, you could use any letter. It doesn't have to be lambda, but that's generally what we like to go with. So there are 3 distinct eigenvalues here for this problem. Okay, now I'm just going to double check that we're filming again since it's been a while since I've done this. Yeah, it looks good. Everything seems to be in focus. Okay. And so now we are on to the eigenvalues, or eigenvectors, right? So on to the eigenvectors. On to the eigenvectors. So now we have to do a problem. We have to do the problem. What is the equation that determines the eigenvectors? A minus lambda I x is 0, right? Okay? So we have to do this for each one of these eigenvalues. So I'm going to do 2, and then I'm going to leave 1 for you to do. Let's look at lambda equals 1. Okay, so we're going to now plug in lambda equals 1 into our matrix A minus lambda I. Okay, so when lambda equals 1, right, then what do we have? A minus lambda I is just A minus 1I. Okay, A minus I. Yeah? Okay, I'll put a little 1 in there. a minus 1I. Well, really, but what am I just going to do? I'm just going to look over here at my matrix with a lambda that's nicely sitting there waiting for me, and I'm going to replace lambda with 1. And so what do I get? 4 minus 1 is 3, 0, 1, negative 2, 1 minus 1, oh, beautiful, 0, right? 0, negative 2, 0, 1 minus 1, 0. Okay, so this is a minus lambda I when I is 1, or when lambda is 1, right? Okay, so now we're trying to solve a minus lambda I x is equal to 0, right? Well, this is just a system of linear equations, yeah? Okay, a matrix times a vector is equal to 0, and my vector, my right-hand side vector is the 0 vector, right? This is a homogeneous system. And so how do I solve homogeneous systems? With my row reductions, yes? And we don't even have to put the augmented matrix here because what is the right-hand side? It's just 0, 0, 0, yeah? So now that you're so good at these row reductions, you know immediately that what you want to do right here is replace row 3 with row 3 minus row 2 becomes the new row 3, right? I'm going to leave row 1 alone, 3, 0, 1. Row 2, we've got negative 2, 0, 0. And then when I take this guy minus that guy, what do I get? 0, 0, 0, right? Okay. Now we're in great shape. If we wanted to then turn this guy into a 1, we could, but we really don't have to do that now. We don't have to go too many steps. We just need to get to a place where we can simply read off what our reduction tells us. So let's go ahead though, just for fun, to replace row 2 with 1 minus 1/2 row 2, just to get a 1 there, and you'll be like, wait, why would we do that? You'll just see in just a sec. And I just wanted to be over here where I have more space, right? So if I do minus 1/2 row 2 becomes my new row 2, right? Then my first row is 3, 0, 1. My next row is minus 1/2, right? 1, 0, 0, and my next row is 0, 0, 0. Yeah? Okay. All right. So let's see what happens here, okay? So this system of equations is equivalent to this coefficient matrix for the same system of equations. So remember what this meant, right? Our x here for this problem, right? X is going to be what size? Right? A is 3 by 3, good. So x is 3 by 1, right? So x is really an x1, x2, x3. Yeah? Okay? So when I get down to here, I'm like, oh, what did this mean, right? It meant, oh, I'm going to multiply this times x1, x2, x3, right? And I'm going to get 0, 0, 0, right? But I've now just simplified this system that I've got a row of zeros. What does my row of zeros say? 0 times x1 plus 0 times x2 plus 0 times x3, that's the left-hand side, right? So my third row says that's equal to 0. 0 is equal to 0. No, that's perfectly fine. That's awesome. That's legit, right? What does my next row say? Row 2 say? It says 1 times x1, right, plus 0 times x2 plus 0 times x3, doing the matrix multiplication, yeah, is equal to 0. So what do I know here? x1 is 0, yeah? All right. Now, what does my next row say? My next row says when I do this multiplication, that times this is equal to that guy. I get 3 times x1 plus 0 times 3 times x1 plus 0 times x2 plus 1 times x3, right, is equal to 0, right? But I just found that x1 is 0, so when I put that in there, right, that tells me then that x3 is also 0, right? Because if x1 is 0, then x3 becomes 0. So what do I discover from this problem, right? I discover that x1 is 0, x3 is 0, and I got no restriction on x2 at all, right? And so what do I know? x2 is anything. x2 is just x2, right? x2 is any real number, right? x2 is free, right? This is my free variable. These guys are my fixed variables, right? So x2 is allowed to roam free. x1 and x3 have to just be 0. And so therefore, what is my x? my eigenvector that goes with the eigenvalue lambda equals 1, right? The eigenvector that goes with that eigenvalue has the form, right? x1, x2, x3. And what is x1 in this case? 0. What is x2? Just itself. And what is x3? 0. Make sense? So any vector that looks like 0, number 0, will be an eigenvector for this eigenvalue, right? What does that mean, right? What was the, ouch. Oh. Okay, anyway, what does that mean, right? Where did we start? Ax equals lambda x, right? That means this matrix A times any vector that looks like this, has 0 in its first and third column, right? Or row, and then doesn't matter what the second guy is, that any vector that looks like that will be the same as just multiplying 1 times that. And so we know that that matrix multiplication will just result in 1 times x2, yeah, in that spot. So the same exact vector. Okay, this guy is my eigenvector then. Eigenvector associated with lambda equals 1, okay? Now, we're going to want to do what we did before, which is, that's what this is right here, okay? That's my eigenvector, x. But we also want to talk about that eigenspace in more generality, and so I can say that this eigenvector, I can factor that x2 out, right? And write it as x2 times 0, 1, 0, yeah? x2 is a real number, some constant, so this is a scalar multiple of the vector 0, 1, 0. Any scalar multiple of the vector 0, 1, 0 is an eigenvector, or lives in the null space of A minus lambda I for lambda equals 1 for this problem, okay? So that's the eigenspace associated with lambda equals 1. And so then we say that the vector 0, 1, 0 is a basis, it's a basis for the eigenspace E1, the set of all eigenvectors associated with lambda equals 1. Everything, the things in the null space of A minus 1 times lambda, okay? So there's infinitely many eigenvectors because this x2 is any real number, right? But we have one basis vector that generates all possible eigenvectors because this is just a scalar multiple of that, a linear combination, but it's only one thing, right? Of that eigenvector. So this 0, 1, 0, a constant vector, is the basis vector. This eigenspace has one basis vector. There's infinitely many eigenvectors because x2 can be any number. Yes? Make sense? Different ways of writing the same thing. Okay? All right, so that was for lambda equals 1. Okay? So now let's do that again for lambda equals, whoops, let me, one of the others, 2 or 3. I guess maybe I'll do 2, you can do 3. Okay, ready? Okay, so now let's do lambda equals 2. Ooh, that one doesn't rate so well. Oops, which one was I using? Hopefully this one. Yeah, much better. Lambda equals 2, okay? So, what do we have to do, right? We want to write down what is A minus lambda I, right? So now A minus lambda I means A minus 2I, right? Well, what is that? Well, really, what do? I just go to my nice A minus lambda I here, and I plug in 2, and then I write down the matrix, right? So when lambda is 2, I'm going to get 2, 0, 1. Negative 2, 1 minus 2 is negative 1, 0, right? And then negative 2, 0, 1 minus 2 is negative 1. Yes? Okay? All right, so now I take a look at this one, and I'm like, okay, what do I do? My goal is, remember, I'm now solving A minus 2I x equals 0, right? So this is just a coefficient matrix in a system of equations for these three variables, right? And I want to simplify this so that I can read off the solutions, right? Read off the answers. All right, well, it's not too hard maybe to notice that the very first thing you might want to do is just replace row 3 with itself plus row 1, right? Because that's going to give me a row of zeros right there. So row 3 plus row 1 gives me my new row 3. And so I don't change row 1, 2, 0, 1. I don't change row 2, negative 2, negative 1, 0. And then what do I get here? 0. I'm doing row 3 plus row 1. Negative 2 plus 2 is 0. 0 plus 0 is 0. Negative 1 plus 1 is 0. So I got my row of zeros. Yes? Okay? That's nice. Okay, so now what? Now what to do? Okay, well, we could nice and simply, if we want, like zero out this guy, right? That's kind of our standard path of zeroing out the lower triangular part of the matrix, right? So let's just do that, okay? Let's do that for fun now. It doesn't matter, we certainly don't want to get a 1 here, right? Because then we'd have to divide by 2 and we'd have fractions, yeah? Okay, we'll do that later. Okay, so let's just replace row 2. We're going to do row 2 plus row 1 replaces row 2, right? Okay, so row 2 plus row 1 replaces row 2. We have a row of zeros for row 3, right? Row 1 stays the same. We're not changing it, right? Okay, and we're going to replace row 2 with row 2 plus row 1, right? So negative 2 plus 2 is 0, right? Negative 1 plus 0 is negative 1, right? 0 plus 1 is 1. Yeah? Okay. So so now we are in reasonably good shape. We don't really need to do much more at this stage. So let's just see what happens if we didn't do anything else at this stage and just wrote down, okay, we now have this system, right? And we're equal to 0, 0, 0. Yeah? Okay. All right, what does the third row tell me? The third row says 0 times x1 plus 0 times x2 plus 0 times x3 is equal to 0. Yeah? That's the matrix multiplication, 0 equals 0, right? I don't have enough room to squeeze these other ones in here, so I'll just write them down, okay? So what does the first row say, right? The first row is saying 2 times x1, right, plus 0 times x2 plus 1 times x3 is equal to 0. Yes? That times that plus that times that plus that times that is equal to that. Yeah? And the second row is saying 0 times x1 plus minus 1 times x2, so minus x2, right, plus 1 times x3 plus x3 is equal to 0. Yeah? It's 0. Okay, so now what do we have? We have x1 and x2, which can both be defined in terms of x3, right? Now there's a lot of different things we can do, but like we said before, we normally are going to keep x3 as our free variable, x1 and x2 as our fixed, okay, in this case. So what happens here? What do we know, right? Let me just come down here because this is, what is this going to say? This is solving this equation for x2, says x2 is equal to x3, right? I bring that to the other side, but write it this way. So we know x2 is equal to x3. And then we're going to solve this one for x1. So 2x1 is equal to minus x3. So x1 is equal to minus 1/2 x3. Yes? Okay? Yeah? What about x3? Well, there are no restrictions on x3, right? x3 is free, right? x3 is the free variable. x1 and x2 are fixed variables, yeah? And so what do we get now from this, right? Our eigenvector x associated with the eigenvalue lambda equals 2 now, right, is, we know it looks like x1, x2, x3, right? Because it's a 3 by 1, yeah? And we know that from our matrix A. And then what did we find out about x1? x1 is minus 1/2 x3. What's x2? x2 is x3. What's x3? x3 is itself, right? x1, x2, x3, yeah? So this is the eigenvector associated with lambda equals 2, okay? What does that mean? Any vector that has the form so that its second and third components are the same and its first component is minus 1/2 of the other component, right, will be such that the multiplication of this matrix times that vector is the same as if I just multiplied that vector by 2, right? And I would get -1 times the first component, 2 times the second component, and 2 times the third component, which is super easy, right? Way easier than doing the matrix multiplication. Yes? Okay? So this is the special type of vector that goes with the eigenvalue 2. These are the eigenvectors associated with the eigenvalue 2. Okay? Again, infinitely many eigenvectors, right? Because x3 is any real number. Yes? So there's infinitely many. Now, what do we want to do? We want to talk about a basis for the eigenspace for the eigenvalue 2. Well, then we want to factor out this guy x3, right? Undo the scalar multiplication of the vector, right? x3 is a scalar, and so what do I have? Minus 1/2, 1, 1. Yes? Okay? So we can then say, let me erase this piece now, give myself a little more space. Again, this is the eigenvector, right? And therefore we can say a basis for the eigenspace E2, the set of all eigenvectors associated with the eigenvalue 2, everything in the null space of A minus 2i, a basis for that space is the vector -1/2, 1, 1. Okay? That's a basis because any multiple, right, any constant multiple of this vector will give me something that's still an eigenvector, right? So it just means that the second and third component have to be the same, and the first component has to be minus 1/2 of what those components are, right? And so there's lots of other bases that we could use, right? Any constant multiple would still be a basis, right? So if we multiply this by 2, so that we don't have to deal with a fraction, we could say a basis for E2 is -1, 2, 2, right? Multiplying that by 2, yeah? So this is one representation of the basis. Here's another representation of the basis, right? Or if you don't want a -1 in the front, right, you can say 1, -2, -2, right? If you multiply that by -1, right? Any of these are a basis for the eigenspace associated with the eigenvalue 2 because they're all just a constant multiple of this, right? Okay? There's only one basis vector, right? We only require a single basis vector, any one of these, multiply that by an arbitrary constant, and you'll have everything in the space, right? And so the eigenspace E2 requires one basis vector. So does the eigenspace, as does the eigenspace E1, the eigenspace associated with the eigenvalue lambda1, right? So we say that the dimension of E2 is 1. The dimension of E1 is 1, right? Dimension is the number of basis vectors you need to represent everything in the space. There are a bunch of different ones we could use as the basis, right? Just like with E1, we had 0, 1, 0. Well, we could use 0, 2, 0 if we wanted. It's the same thing because you're going to multiply it by a constant, right, to get everything in the space. You could use 0 pi 0 if you wanted, right? You generally don't do that, but you could, okay? How many vectors you need to represent everything in the eigenspace is the dimension, okay? So we only need one of them, so you could have multiple different answers for the basis, but as long as they all have the same pattern, right? That the second and third guys are exactly the same, right? And the first guy is minus a half times the second and third, right? Okay. Or you could think about it as the second and third guy is minus 2 times the first guy. Yeah. Okay. Okay. So I will leave the calculation of the lambda equals 3 to you. I will just tell you what the answer is so that you know if you're right. So I'll just say E3 has a basis vector of -1, 1, -1, right? So see if you can produce that for yourself. Oh, no, that's wrong. That would be bad. You wouldn't be able to produce that for yourself. -1, 1, 1. I just can't read my little bracket there, okay? -1, 1, 1, which really basically just says the second and third component have to be the same, and the first component is just negative, whatever those are, right? So again, there's infinitely many others, right? You could say 1, -1, -1. We could say -2, 2, 2, right? Okay. So again, the dimension of the eigenspace E3, the set of all eigenvectors associated with the eigenvalue lambda equals 3 for this matrix, is 1. Okay? And you should be able to say what the eigenvalues all look like, right? The eigenvalues would have 1 free variable, 2 fixed variables. Okay? So I'll let you do that. Let's do another one. Yeah, you ready? Okay. Let me erase. Some space. Okay. So let's do a little 2 by 2. Okay. Let's let A this time be the matrix 10, -9, 4, -2. Okay? So find eigenvalues, evals, eigenvectors, evex, right? And bases for eigenspaces. Okay? Okay, so what do? Well, the first thing we do, right, is we think about what is A minus lambda I. Because the first thing we got to do is find the eigenvalues, right? So we need the characteristic equation for this matrix, right? So A minus lambda I, 10 minus lambda, -9, 4, -2 minus lambda. Yeah? Okay. Now what? Well, we do the equation that gets the eigenvalues. What is the equation that gets the eigenvalues? Good. And why is that the equation that gets the eigenvalues? Yeah. You know, right? Okay. Determinant of A minus lambda I is equal to 0. Yeah? Okay. This is the characteristic polynomial, P of lambda. Okay, so what do we got? We've got 10 minus lambda times -2 minus lambda, right? Doing this determinant. Minus a -36, so plus 36 has to be 0. Yes? Okay, let's see what we do here. How do we solve this? We do not bring the 36 over to this side and set each of these guys equal to 36. That's totally bogus, right? Okay, negative 36. Totally bogus. What do you got to do? You got to turn this into a quadratic, right? And then see if you can factor. And if you can't factor, use the quadratic formula. Okay, so you got to FOIL judiciously here so that you get your lambda squared in the front, right? Minus lambda times minus lambda is lambda squared. Yes? Right? Okay, we all good with that? So I did the L's first, right? Now I'm going to do the mixed terms. So I'll get a minus 10 lambda plus, right? That's a minus there, right? Plus a 2 lambda. Minus 10 lambda plus 2 lambda is minus 8 lambda. Yes? Okay. And then normally what are my lasts, right? 10 times negative 2, right? Negative 20. Yes? Plus 36. So be careful doing these steps, right? Because if you end up with the wrong polynomial, it's going to mess up the entire thing. Okay? So what do we have? Lambda squared minus 8 lambda plus 16 is equal to 0. Does this guy factor? Woohoo! Lo and behold, it does, right? Into what? Lambda minus 4 times lambda minus 4. Yeah, so lambda minus 4 squared. So what do we end up with here, right? Lo and behold, lambda equals 4 is a double root, right? Repeated root. Well, what's going to happen in that case? Well, you don't know, right? You guys got to go ahead and find out, okay? So this guy is our only eigenvalue. So this matrix is 2 by 2, A is 2 by 2, right? This matrix has only one eigenvalue. Lambda equals 4, and it's a double root, right? Now the characteristic polynomial is all, you may have noticed, right? Here the characteristic polynomial was a quadratic equation for lambda. That has 2 roots, right? Just like this is a 2 by 2 equation, yeah? Okay, so the characteristic polynomial is going to be that dimension, whatever n is, and you got that many roots. But you could have repeated, you could have distinct, you could have complex conjugate pairs, right? All right, in the last example, n was 3, we had a cubic polynomial, it factored into 3 distinct roots. Here we've got a repeated root. Okay, so what do? We're kind of happy, right? Because you only have to do this one time to look for the eigenvalues, right? Or the eigenvectors, right? Here's the equation for the eigenvectors. And again, what are we looking for, right? We're looking for ax equals lambda x. And what is x now? X is just x1, x2, right? Because x is 2 by 1, because we have a matrix A, which is 2 by 2. So we need to look at our lambda equals 4 and plug it in, right? And write down what is A minus lambda I, right? So that's just A minus 4I. We're not actually computing that. We're just plugging into our nice little, expression that we have sitting right here waiting for us. So when lambda is 4, 10 minus 4 is 6. And then I've got negative 9. Then I've got a 4, right? Then we've got minus 2. Minus 4, right? So a minus 6. Yeah? Okay. All right, well, let's just simplify our numbers for a minute, right? So these guys are multiples of 3, so I can do 1/3 R1 is my new R1, right? And so if I divide by 3, right, I've got 2 and negative 3. And then I can do 1/2 R2 is my new R2, yeah, just to simplify the numbers, right? And then what do I get? Lo and behold, right, 2, negative 3. Wait, what happened? Woo, okay, yeah, right? All right, we good here? Okay. So now what? We're super happy, right? We replace row 2 with row 2 minus row 1, right? And lo and behold, we have 2, negative 3, 0, 0. Yes? Okay, you guys good? All right, we have a row of zeros, so we're done. And remember what we were doing? We were solving this equation for the eigenvalues, or the eigenvectors, right? And we should say like the only eigenvalue. Okay, And so what does this equation mean? Remember, it was a homogeneous equation. X was a 2 by 1 column vector this time, and I'm setting that equal to 0, 0, right? The bottom row is just telling me 0 times x1 plus 0 times x2 is equal to this 0, so I get 0 equals 0. And the top row is telling me 2 times x1, right, minus 3 times x2 is equal to 0. Yes? 2x1 minus 3x2 is equal to that 0. Okay, so what do? I solve for 2x1 is equal to 3x2, yeah, or x1 is 3 halves x2, right? So here, x1 is my fixed variable, x2 is my free variable, and x2 is allowed to be any real number, right? There's no equation that puts a restriction on x2. So what is our eigenvector then that goes along with this eigenvalue? The eigenvector x looks like x1, x2, right? Well, what is x1? x1 is 3 halves x2, right? What is x2? Itself, yeah? So again, what were we doing here, right? Ax equals lambda x. That equation has only one eigenvalue, one scalar, which is 4, for which there exist values, vectors x, such that multiplying this matrix times x will result in just scaling the vector by 4, okay? Those vectors x have to look like the first component is 3 halves whatever in the second component, yeah? Okay? Another way to write that, right, is if I multiply, well, let's just do what we've been doing. Let's factor out the x of 2, yeah? And that's then 3 halves and 1, right? So again, infinitely many eigenvectors associated with the eigenvalue 4, right? Any vector, that's a column vector, whose first component is 3 halves times its second component, right? X2 can be any real number, and so then we say, right, a basis for E4, right, the eigenspace associated with the eigenvalue 4 is, well, we could say 3 halves 1 if we want, right, because I was just reading it right off of there, right? Or if I wanted, and I didn't like the fractions, I could just multiply it by 2 and I could say 3, 2. Yeah? Does that make sense? But there's still only one basis vector required, and so the dimension of E4 is 1. One basis vector required. So that's kind of weird, right? So when we had our previous example where A was a 3 by 3 matrix, we had 3 distinct eigenvalues. Each one had an eigenspace that required one basis vector for their eigenspaces. So the total number of the dimension, the total number of basis vectors needed for all of the eigenvectors, all the eigenspaces, was 3 in that case, and 3 was the dimension that n was, right? And it was a 3 by 3 matrix, right? But here we have a 2 by 2, but the dimension of our only eigenspace is 1. And the question is, well, what's going on there? Shouldn't it have been 2? Like, what happened? Is that all because there's a double root? If there's a double root, do you always end up with like 1 less? No, the answer is no. And so you have to go ahead and work things out and figure out what you get, okay? So sometimes when you get a repeated root, you only get 1 basis vector, but sometimes you get 2, okay? If we were in a 3D problem, right, where our x was in R3, if we have a triple root, you could either get 1 basis vector, 2 basis vectors, or 3 basis vectors, okay? So I guess I will wait on that. Let's see. Let's do another problem. Okay, let's do another problem. Although, actually, what I think I'm going to do is just end this video so I can make these videos slightly shorter, and then we'll come back and do something else in another video. So I will see you again soon.